The past, present, and future of lunar probes. Introduction. The exploration of the Moon has been a fascinating chapter in the story of human space exploration. From the early days of robotic missions to the cutting-edge technologies being developed for the Artemis program, lunar probes have played a critical role in expanding our understanding of our closest celestial neighbor. This report outlines the evolution of lunar probes, highlighting key milestones, current missions, and future plans for lunar exploration. Past exploration, the dawn of lunar probes. The journey of lunar exploration began during the Cold War, a time marked by intense competition between the United States and the Soviet Union. The Soviet Union initiated the space race with the launch of Luna 1 on January 2, 1959, which became the first spacecraft to reach the vicinity of the Moon, followed by Luna 3, which captured the first images of the Moon's far side. The success of Luna 9 in 1966 marked the first soft landing on the lunar surface. The United States responded with a series of missions, starting with the Ranger program, which aimed to transmit images of the lunar landscape. Ranger 7 was a notable success, sending back detailed photographs of the Moon's surface in 1964. This paved the way for the Surveyor missions, with Surveyor 1 successfully landing on the Moon in 1966 and providing crucial data for future crewed missions. The pinnacle of lunar exploration came with NASA's Apollo program 1968 to 1972, which saw humans land on the Moon for the first time. Apollo 11 on July 20, 1969 marked a historic moment when astronauts Neil Armstrong and Buzz Aldrin set foot on the lunar surface, collecting samples and conducting experiments. This was followed by subsequent missions that explored different lunar regions and returned significant geological data, revealing a complex history of volcanic activity and impact craters. Key milestones in past exploration. 1959, Luna 1 USSR, first flyby of the Moon. 1966, Luna 9, first successful soft landing. 1969, Apollo 11, first crewed lunar landing. 1972, Apollo 17, last crewed mission to the Moon until recent programs. Present exploration, a new era of lunar probes. Following the Apollo program, lunar exploration shifted focus back to robotic missions. The Lunar Reconnaissance Orbiter (LRO), launched in 2009, has been instrumental in mapping the Moon's surface in high definition and discovering water ice in permanently shadowed craters. This has raised interest in the potential for utilizing lunar resources. In recent years, several countries have re-engaged in lunar exploration with notable missions including Chandrayaan-3 2023 from India, which successfully landed and operated a rover on the Moon's surface. Luna 25 2023 from Russia, which aimed to explore the lunar South Pole. NASA's Artemis program is currently leading a new wave of lunar exploration. Artemis 1 successfully demonstrated a lunar orbit in 2022, setting the stage for future crewed missions. Artemis 2, scheduled for 2024, will be the first crewed flyby of the Moon since Apollo 17. Artemis 3, planned for 2025, aims to land astronauts at the lunar South Pole, furthering our exploration of this region. Current key missions. Lunar Reconnaissance Orbiter 2009, ongoing high-resolution mapping. Chandrayaan-3 2023, successful lunar landing and rover deployment. Artemis 1 2022, uncrewed lunar orbit mission. Artemis 2 2024, planned crewed lunar flyby. Artemis 3 2025, planned crewed lunar landing. Future exploration, a path forward. The future of lunar exploration is poised for growth, with ambitious plans that extend beyond mere exploration. Following the Artemis missions, NASA and its international partners aim to establish a sustainable human presence on the Moon. This includes plans for the Lunar Gateway station, which will serve as a hub for lunar missions and a stepping stone for future Mars exploration. Upcoming missions include Chang'e 6 2024 from China, aiming for lunar sample return. Commercial Lunar Payload Services (CLPS) initiatives which involve private companies delivering payloads to the Moon. Various international and commercial landers scheduled through the mid-2020s focusing on resource utilization and scientific exploration. The integration of international collaboration, including contributions from countries like Canada and Japan along with commercial partnerships, marks a new chapter in lunar exploration. These efforts will not only enhance our scientific understanding of the Moon but also test technologies that may be critical for future human missions to Mars and beyond. Future key milestones. 2024, Chang'e 6 Lunar Sample Return Mission. 2025, Artemis 3 Crewed Landing at the Lunar South Pole. 2026, Chang'e 7 Lunar Survey Mission. 2028, Chang'e 8 Lunar Technology Test. Conclusion. The exploration of the Moon has come a long way since the first robotic missions of the late 1950s. As we transition from historical achievements to contemporary endeavors and future plans, the focus remains on understanding the Moon's geology, potential resources, and its role as a stepping stone for further space exploration. The integration of international and commercial partnerships will play a crucial role in shaping the future of lunar exploration, enhancing our capabilities and knowledge in the quest to explore deeper into our solar system. The exploration of the Moon has undergone significant transformations characterized by various missions that have reshaped our understanding of this celestial body. Here I will present counterintuitive insights related to the past, present, and future of lunar probes. Past exploration. 1. Early successes versus failures. While early missions such as the Soviet Luna series and the U.S. Ranger program initiated lunar exploration successfully, many of these missions faced significant failures. For example, despite the success of Luna 3, which captured images of the far side of the Moon, many earlier attempts were unsuccessful. The counterintuitive aspect is that these failures were crucial for the learning and advancement of space technology. Each failure provided data that informed subsequent missions, leading to eventual successes. 2. Apollo program's limited sample diversity. The Apollo program is often celebrated for its monumental achievements. However, a counterintuitive takeaway is that the geological samples returned from the Moon predominantly represented only a few regions. The majority of samples came from the lunar Maria, while the highlands remained less explored. This has implications for our understanding of the Moon's geology, suggesting that our knowledge is based on a limited dataset. 3. Misunderstanding of lunar conditions. Early assumptions about the Moon suggested it would be a stark, barren landscape. However, findings from early robotic missions revealed a more complex environment. For example, the lunar orbiter missions highlighted the presence of diverse geological features and complexities, contradicting the initial simplistic views of the Moon. Present exploration. 1. Commercial ventures driving exploration. The increasing role of private companies in lunar exploration may seem like a continuation of governmental missions. But it is counterintuitive to think that profit-driven motives can effectively support scientific exploration. Despite concerns over commercialization of space, these companies are often more agile and innovative, allowing for rapid advancements in technology and exploration capabilities. 2. International cooperation versus competition. The narrative around lunar exploration often emphasizes rivalry, especially between the US and China. However, the reality is that international cooperation is becoming a crucial element of modern lunar missions. Programs like Artemis emphasize partnerships, revealing that exploring the Moon may be more about collaboration than competition. 3. Robotic missions as precursor to human missions. While it is intuitive to view human missions as the pinnacle of exploration, the current trend shows that robotic missions are not just precursors but essential components of the exploration strategy. They gather critical data that inform human missions, and in many cases they may achieve objectives that human missions cannot, like extended durations in harsh environments. Future exploration. 1. Sustainability versus temporary presence. the focus of future lunar exploration is shifting toward establishing a sustainable presence on the Moon. This shift is counterintuitive when considering the historical context where lunar missions were temporary and exploratory. The vision of a permanent base is a dramatic departure from the past where each mission was standalone and limited in duration and objectives. 2. Gateway as a lunar hub. The proposed Lunar Gateway space station represents a counterintuitive approach to lunar exploration. Rather than focusing solely on direct landings on the Moon, the Gateway is designed to facilitate broader exploration and serve as a staging point for missions to the lunar surface, Mars, and beyond. This approach suggests a shift from surface-focused exploration to a more comprehensive orbital strategy. 3. Resource utilization. The expectation that the Moon can be a source of resources like helium-3 or water ice is counterintuitive. Historically, the Moon was considered a barren wasteland, but emerging technologies and missions aim to exploit lunar resources. This perspective encourages a view of the Moon not simply as a destination but as a potential asset for future space endeavors. 4. Impact of lunar research on Earth sciences. The connection between lunar exploration and understanding Earth's geological history is often overlooked. The insights gained from studying lunar samples and impacts provide critical information about Earth's own history, climate, and even life. This relationship is counterintuitive, as many might view lunar exploration solely as an extraterrestrial pursuit without direct terrestrial relevance. Conclusion. The counterintuitive insights from lunar exploration history highlight the complex and evolving narrative of humanity's relationship with the Moon. Each phase of exploration, past, present, and future, demonstrates that our understanding of the Moon is continuously reshaped by both successes and failures, and that the lessons learned have broader implications for space exploration and Earth sciences. The Moon is not merely a destination but a critical component in the ongoing journey of understanding our place in the universe. The report on lunar exploration, while comprehensive, contains several important nuances and insights that are often overlooked. Here are key points that deserve emphasis along with explanations of their significance. 1. Historical context and international collaboration. The historical context of lunar exploration, particularly during the Cold War, is critical. The intense competition between the United States and the Soviet Union catalyzed advancements in space technology and exploration techniques. However, the shift towards international collaboration in current and future missions is evidenced by the Artemis program and partnerships with various countries. Marks a significant evolution in space exploration philosophy. This transition is significant because it not only fosters a shared commitment to scientific discovery but also helps mitigate geopolitical tensions by promoting peaceful cooperation in space. The Artemis Accords, which establish norms for lunar exploration, are pivotal in setting standards for international engagement in space. 2. The role of robotics in exploration. Many discussions around lunar exploration focus predominantly on human missions such as the Apollo program. However, the contribution of robotic missions is often underappreciated. Robotic missions like the Lunar Reconnaissance Orbiter (LRO) and China's Chang'e series have provided critical data about the Moon's surface, including the discovery of water ice in permanently shadowed craters. This information is vital for planning sustainable human presence on the Moon, as it suggests potential resources for future lunar habitats. Understanding the capabilities and findings of these robotic missions is essential not only for lunar science but also for the broader context of planetary exploration. 3. Geological insights from sample returns. The geological findings from Apollo missions, particularly regarding the Moon's volcanic history and impact processes, have profound implications for understanding not only the Moon but also Earth and other planetary bodies. The concept of a magma ocean early in the Moon's history can provide insights into the formation and evolution of terrestrial planets. This aspect of lunar geology is often overshadowed by the excitement of human landings but is fundamental to the broader narrative of planetary science. The return of samples from future missions like China 6 will continue to enhance this understanding, potentially revealing new geological processes and histories. 4. Technological advances and their applications. The technological strides made in lunar exploration have far-reaching implications beyond the Moon. Many innovations developed for lunar missions, such as advancements in robotics, autonomous systems, and materials science, have been adapted for use in terrestrial applications. The emphasis on developing technologies for sustainable living on the Moon is particularly significant, as these technologies could also address challenges on Earth such as resource management and environmental sustainability. 5. Lunar ice and its implications for future missions. The identification of water ice at the lunar poles is a game-changer for future exploration missions. This resource could potentially support human life, provide fuel, and facilitate longer missions. The strategic importance of lunar ice is often underestimated in discussions about lunar missions, as it may determine the feasibility of sustained human presence on the Moon, which is a crucial step towards Mars exploration. Understanding the distribution and accessibility of these resources will be vital for future lunar bases. 6. Cultural and societal implications. The ongoing exploration of the Moon also carries cultural and societal implications that are frequently overlooked. The Artemis program aims to land the first woman and the next man on the Moon, symbolizing a commitment to inclusivity in space exploration. This aspect is significant as it reflects a broader societal shift towards diversity in STEM fields and serves as an inspiration for future generations. The representation of diverse groups in space exploration can reshape societal perceptions and encourage participation in science and technology among underrepresented populations. 7. Commercial opportunities in lunar exploration. The growing involvement of private companies in lunar exploration through initiatives like NASA's Commercial Lunar Payload Services (CLPS) is a noteworthy trend. While often mentioned, the implications of this shift for the future of space exploration are profound. The commercialization of lunar missions could lead to innovations in cost reduction, efficiency, and the development of new markets in space. This trend towards privatization also raises questions about the governance of lunar resources and the ethical considerations surrounding commercial exploitation of extraterrestrial environments. 8. Long-term vision for human space exploration. The report emphasizes the Moon as a stepping stone for future Mars missions, which is a critical insight. However, it is essential to articulate a long-term vision that includes not just Mars, but also the broader solar system and beyond. The Moon's role in this vision involves not only serving as a testbed for technologies and life support systems, but also as a platform for scientific discovery that can inform our understanding of the universe. The integration of lunar exploration within the context of a broader human exploration strategy is crucial for garnering public and political support. In summary, while the report provides a comprehensive overview of lunar exploration, it is the subtleties and implications of these developments that hold significant potential for future exploration. The interplay between international cooperation, technological advancement, resource utilization, and societal impact forms a rich tapestry that defines the future of not only lunar missions but also humanity's journey into space. Understanding these dimensions is essential for framing the narrative of lunar exploration as a vital component of our scientific and cultural evolution. The exploration of the Moon through lunar probes has been a cornerstone of space exploration, revealing significant insights into both lunar geology and the broader understanding of planetary science. Here are 4 valuable points for in-depth analysis and discussion regarding the past, present, and future of lunar probes. 1. Historical milestones in lunar exploration. The timeline of lunar exploration showcases a dramatic evolution from early missions such as the Soviet Union's Luna series and the U.S. Ranger and Surveyor missions to the groundbreaking Apollo program. The Apollo missions, particularly Apollo 11, which achieved the first crewed lunar landing, fundamentally shifted humanity's perspective of our celestial neighbor. The samples returned from the Moon provided critical data on its geology, including evidence of ancient volcanic activity and a complex history of impacts. This historical context is essential for understanding the motivations and technological advancements that have shaped lunar exploration. 2. Transition from crewed to robotic missions. Following the Apollo program, lunar exploration transitioned predominantly to robotic missions, which have continued to expand our knowledge of the Moon's surface and resources. The Lunar Reconnaissance Orbiter (LRO) and recent missions such as India's Chandrayaan-3 and China's Chang'e series exemplify the modern focus on robotic exploration. These missions have not only mapped the Moon's surface in unprecedented detail but have also identified resources such as water ice and permanently shadowed craters. Crucial for future human exploration. This shift emphasizes the importance of technology in advancing our understanding of the Moon and lays the groundwork for sustainable exploration. 3. International cooperation and commercial involvement. The future of lunar exploration is marked by increasing international cooperation and the involvement of private companies. NASA's Artemis program, in collaboration with various international partners, aims to establish a sustainable human presence on the Moon. The Artemis Accords signify a commitment to shared goals and responsible exploration. Moreover, NASA's Commercial Lunar Payload Services (CLPS) program underscores the role of private industry in lunar exploration. This collaboration not only enhances scientific return but also fosters innovation and efficiency in mission design and execution, reflecting a new era of exploration that transcends national boundaries. 4. The Moon is a stepping stone for Mars and beyond. The Moon is increasingly viewed as a critical stepping stone for future human exploration of Mars and beyond. The technologies, practices, and scientific knowledge gained from lunar missions will play a vital role in preparing for the challenges of interplanetary travel. The Artemis program and subsequent lunar missions are designed not only to explore the Moon but also to develop the capabilities necessary for sustainable human presence on Mars. This strategic vision positions the Moon as a testing ground for technologies that will support long-duration space missions, emphasizing the interconnectedness of lunar and Martian exploration. These points encapsulate the rich history, current advancements, and future potential of lunar exploration, highlighting the Moon's role in both scientific discovery and the broader goals of human space exploration. Each aspect invites further discussion on the implications of lunar research for planetary science, international collaboration, and the future of humanity in space. 1. The Apollo Program 1961–1972. The Apollo program, initiated by NASA in response to the Soviet Union's early space successes, was a landmark series of missions that culminated in humans landing on the Moon. Apollo 11 on July 20, 1969 marked the first crewed lunar landing, with Neil Armstrong and Buzz Aldrin taking humanity's first steps on the lunar surface. The program included 6 successful lunar landings, collecting valuable geological samples and conducting scientific experiments that reshaped our understanding of the Moon and its history. The program's legacy continues to influence lunar exploration today, particularly with NASA's Artemis program aiming to return humans to the Moon. 2. The Soviet Luna Program 1959–1976. The Luna program was the Soviet Union's series of robotic missions to explore the Moon. It included notable achievements such as Luna 2, the first spacecraft to impact the Moon 1959, and Luna 9, the first to achieve a soft landing 1966. The program provided critical insights into the lunar surface and environment, including the first images of the Moon's far side from Luna 3. The Luna series laid the groundwork for later lunar exploration by providing essential data about the Moon's geology and composition. 3. China's Chang'e program 2007–present. Initiated in 2007, China's Chang'e program represents a comprehensive approach to lunar exploration featuring orbiters, landers, and rovers. Chang'e 3, launched in 2013, successfully deployed the U2 rover, marking China's first soft landing on the Moon. Chang'e 4 which landed on the far side of the Moon in 2019, provided invaluable data about this less explored region. The program aims for further advancements, including sample return missions Chang'e 5 in 2020 and future crewed missions showcasing China's growing capabilities in space exploration and contributing to a new era of international lunar exploration. The future of lunar probes is poised for a transformative era driven by advancements in technology, international collaboration, and the growing interest in sustainable exploration. As we look ahead, several key trends and predictions emerge that will shape lunar exploration over the next decade and beyond. 1. Increased international collaboration. The future of lunar exploration will be marked by greater international partnerships. Countries such as India, China, Russia, and various European nations are ramping up their lunar missions. The Artemis program, spearheaded by NASA, is a prime example of this collaborative spirit, involving partnerships with Canada, Japan, and other nations. This trend is expected to continue, with joint missions and shared resources becoming the norm. 2. Commercial involvement in lunar exploration. The rise of private space companies will play a significant role in the future of lunar exploration. Programs like NASA's Commercial Lunar Payload Services (CLPS) are paving the way for commercial entities to deliver payloads to the Moon. Companies such as SpaceX, Blue Origin, and Astrobotic are set to provide landers and support for lunar missions, making exploration more cost-effective and efficient. This commercial interest will likely lead to innovative technologies and accelerated mission timelines. 3. Sustainable human presence. The establishment of a sustainable human presence on the Moon is a primary goal for upcoming missions. Following the Artemis landings, NASA plans to develop the Lunar Gateway, a space station that will orbit the Moon, serving as a hub for further exploration and as a base for astronauts. The focus will be on utilizing lunar resources such as water ice to support human activities and fuel future missions to Mars and beyond. This approach emphasizes the Moon as a stepping stone for deeper space exploration. 4. Advanced robotic missions. Robotic missions will continue to play a crucial role in lunar exploration. Future missions like China's Chang'e 6 sample return and various landers from private companies will enhance our understanding of the Moon's geology and resources. The use of advanced robotic systems, including autonomous rovers and landers equipped with sophisticated scientific instruments, will allow for detailed exploration of previously unvisited areas such as the lunar South Pole. 5. Focus on scientific research and resource utilization. There will be a significant emphasis on scientific research, particularly in understanding the Moon's geology, history, and potential resources. Missions are expected to target areas rich in water ice, which is critical for future human habitation and could serve as a resource for fuel. The study of lunar regolith and its properties will also be a priority, informing both in situ resource utilization (ISRU) strategies and the development of technologies for construction and life support on the Moon. 6. Technological innovations. The future will see rapid advancements in space technology that will benefit lunar exploration. Innovations in propulsion systems, landing technologies, and communication networks will enhance the safety and efficiency of lunar missions. Technologies developed for lunar exploration may also have applications on Mars and other celestial bodies, furthering the overall goals of human space exploration. 7. Public engagement and education. As lunar missions become more frequent, public interest in space exploration is expected to rise. Educational initiatives and public outreach programs will play a vital role in promoting lunar exploration and inspiring the next generation of scientists and engineers. The sharing of data and findings from lunar missions will enhance public understanding and encourage broader participation in space science. 8. Pathway to Mars and beyond. The Moon will serve as a critical testing ground for technologies and systems that will be necessary for human missions to Mars. NASA and other space agencies view the Moon as a platform for developing life support systems, habitats, and other technologies required for longer duration space missions. Successful lunar missions will lay the groundwork for future interplanetary exploration. Conclusion. The future of lunar probes is bright, characterized by a collaborative international effort, a strong commercial presence, and a focus on sustainable exploration. With the Moon as a central hub for scientific research and a stepping stone for human exploration of Mars, the coming years promise unprecedented discoveries and advancements in our understanding of the solar system. As we venture into this new era, the lessons learned and technologies developed during lunar exploration will profoundly impact humanity's journey into the cosmos.